Hello and welcome to the 6th lecture of analog integrated circuit design. At the end of the previous class, we were looking at the effect of delay in a negative feedback system. We were looking at it qualitatively. In this lecture, we will do so quantitatively in this one and the next few lectures. When we were looking at the negative feedback system with delay, basically the feedback is delayed. That means that the comparison with the input is with the actual output not at this instant, but at some time ago. So, the disadvantage of this is that we do not know if the desired output, if the actual output has reached the desired target or if it is yet to reach because of the delay. Because of this, there is a possibility that the output goes beyond the desired value. So, that means there is an overshoot, and sometimes this overshoot can persist for some time and results in a phenomenon known as ringing. That is, you can go past the desired target and you will realize it only later, then you will start coming down, then you will go below the desired target and go back up and so on, and this can happen repeatedly and this is undesirable. So, what we need to do now is to analyze the negative feedback system with delay and see the values of delays that are tolerable, because we can easily imagine that if the delays are very small, everything will be fine. We have to put a quantitative limit to the delay that is allowed in the negative feedback system, so that we can design our negative feedback systems to behave properly. Okay. This is our negative feedback amplifier. The output voltage is divided by K and compared with the input Vi. This is what we have analyzed so far. We have seen that if the input is a constant and the output, if it starts from any other value, will reach K times the input value. Okay. Now, a delay can appear in any part of the system. It can appear in the integrator due to the implementation of the integrator, or it can appear in the feedback. It does not matter where it is, the delay is the same. So, for now I am going to assume that the delay appears in the feedback path. That is, instead of this model, I am going to use a model with an additional delay. Okay. So, this additional delay is Td. So, now we have to analyze the system. Just like before, we are going to write the differential equation for this system and then analyze the system. Okay. We see that here we get V naught by K, and because we have delays, I will make the time dependence explicit. So, what appears at the feedback point is delayed V naught divided by K, and now things are very simple. If the output is V naught, the input to the integrator has to be 1 over omega u, the time derivative of V naught. So, it is very easy to write the differential equation. The input of the integrator equals the input minus the delayed output divided by K. Okay. This is the differential equation that we have to solve. Now, let me put down the differential equation again. Previously, when we solved the equation without delay, we assumed that the output is initially at 0 and then saw what happens when an input is applied to it. The input is initially 0, the output is also 0, and then the input steps to say 1 volt, then we see what happens to the output. Now, just for simplicity, I will assume the opposite for now. I will assume that the input is 1 volt, and I will also assume that the output has reached a steady state of k volts, that is the output corresponding to 1 volt. The feedback quantity here is 1 volt and here also it is 1 volt. So, the input of the integrator is 0 and the output has reached steady state. Okay. I will assume that that is what was the case before t equal to 0, and at t equal to 0 Vi steps to 0. Okay. So, the output is still at k volts and we want to see how it comes down. Okay. And the reason to do this is rather simple, that I would like to simply eliminate this term for the time period that I am solving. Okay. This is the steady state which has been reached before t equal to 0. Now, at t equal to 0, Vi goes to 0, and we want to solve this differential equation for t greater than 0. So, because Vi steps to 0, the equation is simplified. And once things become simpler, it becomes easier to visualize the solution. Okay. So, first before we go and try to solve this, let us see what kind of a solution we can expect. Okay. So, before we had solved an equation without this Td, that is 1 over omega u dV naught by dt equals minus V naught of t by k, and the solution to that was an exponential. Okay. So, now we can see what is the kind of solution this kind of an equation permits. So, here we will not be discussing solving differential equations in general, but we would like to find out the solution of this particular differential equation. Okay. So, what is this equation saying? Now, without delay, the equation would have been so to solve this type of stuff, of course, you can use your knowledge of solutions of differential equation to solve it, but it also helps to have a picture of what the equation is saying, so that you can guess at the kind of solution. Okay. First, we will do it for the case without delay. So, this I can manipulate it to be now. Also, you notice that this part omega u divided by k is a scaling factor, and the solution of the differential equation will remain the same whether you have the scaling factor or not, because it is a linear differential equation. So, what the here I have rewritten the equation without the scaling factor, and what the equation is really saying is that the time derivative of the function is the same as the function. Okay. I have omitted a minus sign here, but that can again be absorbed into the scaling factor. So, what the equation is saying is that the time derivative is the same as the function itself. Now, even if you did not know how to solve differential equations, you could have done this, like for instance after high school where you learn about differential coefficients, when you learn about differentiation, you have a table of functions and its derivatives. So, you look at the table and see which of the entries of the table has the same column, same on the left column and the right column. Which of the entries of the table has the same function on the left column and the right column, and the answer is obvious, it is of the form of the exponential. Okay. And then you have to add some scaling factors to make the complete equation be satisfied. Okay. Now we can look at our case, that is the differential equation including the delay in a similar way and try to find the solution. So, although this looks different from before, it is more or less the same. I will rearrange the terms as follows, and I will rewrite it without the scaling factor. Okay. So, what this equation is saying is that the derivative of the function V naught is the same as the delayed function. So, again with a little bit of knowledge of functions and their derivatives, you will be able to easily see that an exponential satisfies this relationship, because an exponential that is delayed is still an exponential with a scaling factor. Okay. So, an exponential will again satisfy this, and we will have to find the right parameters of the exponential, so that this equation is satisfied. So, that is what I am going to do now. Okay. So, to quickly summarize what we did, we have written down the differential equation for the negative feedback amplifier with a delay in the feedback path. Then we have not yet solved it, but we have tried to find the nature of the solution, and the equation when reduced to the bare essentials simply says that the derivative is the same as the delayed function, and from that we can guess that the solution is of the form of an exponential. So, now we will plug the exponential into this equation and see the parameters of the exponential that are required, so that the equation is satisfied. Okay. So, I will assume that V naught is an exponential. There will be some scaling factor, which let me just call it Vp exponential, and I will call this sigma t. Okay. Assuming this, I can rewrite the differential equation and I get Vp sigma exponential of sigma t is dV naught by dt, and it is the same as minus Vp exponential of sigma t minus Td divided by k. Okay. And which in turn can be written as minus Vp exponential of sigma t exponential of minus sigma Td divided by k. Okay. So, you very easily see that Vp exponential of sigma t cancels out, and what you are left with is sigma by omega u equals minus exponential minus sigma Td divided by k. Now, I am going to show the solution to this. It cannot be solved in an explicit form. I cannot write sigma equal to something, but we can look at the function and try to solve for sigma numerically. But before I do that, I would encourage you to pause the lecture at this point and try to solve the equation yourself. Okay? Because it is only when you solve all the steps of the problem yourself that you will be able to fully understand the solution. I will recast it as okay. Now, I will redefine the variables. You know that because you have sigma t in the exponential, sigma has dimensions of frequency, and in this form it is normalized to omega u by k. Okay. So, let me rewrite this. I will normalize sigma to omega u by k plus I get exponential minus sigma t d, but I am going to rewrite this as sigma by omega u by k times t d times omega u divided by k. It is exactly the same, it is equal to sigma t d. I have just normalized everything to omega u by k. Now, the reason for this will become clearer later, but you already know that k divided by omega u is the time constant of the system, and omega u divided by k is the bandwidth of the system when there are no delays. So, essentially we are normalizing everything, we are normalizing the frequency to omega u by k and time to k by omega u, which is the time constant of the system. This leaves all the variables dimensionless and it becomes less messy to handle. So, I will define sigma prime to be sigma by omega u by k, and I will define a normalized delay tau, which is T d divided by k by omega u. And rewriting in terms of the new variables, I have sigma prime plus exponential of minus sigma prime tau to be 0. And if we know how much delay T d there is, we already know omega u and k. So, we know tau in this equation and we have to solve for sigma. Again, I would encourage you to pause at this point and plot this function yourself and try to find the zeros of the function. Plot this function sigma prime plus exponential minus sigma prime tau versus sigma, and you will be able to get an idea of what solutions there are to this system. Okay. And to visualize this, it will be useful to plot this function versus sigma prime. Before we go there, we can substitute tau equal to 0, which is the case without delay, and see what happens. If tau equals 0, we have sigma prime plus 1 is 0, that is sigma prime to be minus 1 or sigma to be minus omega u by k. And this we already know to be the right answer, because when we solved the system without delay, we had got exponential of minus omega u by k times t. Okay. And this is another useful practice, because as you go along you will solve more and more complicated problems, and when you set up the equation for a more complicated problem, it always pays to reduce it to the simpler case by setting some of the variables to the simpler case, and make sure that the complicated equation that you have set up indeed is passing the sanity check, at least it satisfies the simpler case. Then you can go on to solve the more complicated case. Okay. So, now we will go ahead and plot this particular function versus sigma prime. First, I will plot the two parts of the function separately. Sigma prime versus sigma prime is nothing but a straight line passing through the origin. So, this is the first part of the function. Okay. Now, for the second part of the function, exponential of sigma prime tau, this depends on what tau is. When sigma prime is 0, this is always unity, and if tau is very small, it will be a shallow curve like this, and if tau is very large, it will be a steep curve like that. Okay. And a special case that we can also look at is tau equal to 0. Okay. So, for tau equal to 0, what do you see? Simply we see the sum of this straight line, the blue one and the green dashed one, and we will get the sum to be something like that, okay, and it crosses 0 at -1. We already know that the solution for T d equal to 0 is sigma prime of -1 or sigma of minus omega u by k. So, with reference to this, we can see what happens to the other cases. For a small value of tau, what happens is that for positive value of sigma prime, for a large value of sigma prime, the exponential goes to 0 and this curve, the sum of the two approaches the straight line. Okay. So, we will get a curve that is something like, it keeps approaching the blue straight line, and then for negative values of sigma prime, it does something like that, it goes to 0, but for very large and negative values of sigma prime, the exponential takes over. The exponential for negative values will be like that. So, this comes back up and follows the exponential. Okay. So, as you can see, there are two things to observe. One is that the roots will be both more negative than -1. Okay. So, you will have a root here and you will have a root here, and there will be two of them, because for positive values of sigma prime, the straight line is dominant, and finally, the sum approaches the straight line, and for negative values of sigma prime, the exponential is dominant and the sum approaches the exponential, and in the middle somewhere it reaches a minimum, and the minimum can go below 0, and for very small values of tau it does go below 0, and there will be two solutions, both of which are more negative than -1. Okay. Now, for a very large value of tau, what happens is that if you look at this orange case, then on the positive side it quickly approaches the straight line, not much interesting there, but on the negative side what happens is it does come below, but then the exponential is rising so fast that it goes up very quickly without ever reaching 0. Okay. So, this is what we can tell by a little bit of qualitative examination of this particular function. For tau equal to 0, we get a solution of sigma equal to -1. There is only one solution, because this straight line goes off to larger and larger negative values, and for small values of tau, there are two solutions, both of which are more negative than -1, that can be got from this red dashed line, and for large values of tau, there will be no solution at all. That is, if we assume a function of this type, exponential of sigma t for our solution with respect to time, there will be no solution at all. We will see what to do about that case later. We will also see what is the value of tau for which there will be no solution. Okay. But when there is a solution, there will be two of them, both of which are more negative than -1. Okay. So, for the case of negative feedback with delay, what happens is that we get an equation of this form. We assume a solution which is exponential sigma t, and that results in an equation of this form, where sigma prime is the normalized sigma and tau is the normalized delay, and this particular equation has two solutions for small values of tau, and again tau is the delay in the system normalized to the time constant. Okay. So, if the delay is much smaller than the time constant, then there are two solutions, and let me call this sigma 1 prime and sigma 2 prime. These give to sigma 1 and sigma 2 when you undo the normalization. Okay. And it has no solutions for large tau, and we can also calculate the largest value of tau for which there are solutions. Okay. In other words, the value of tau beyond which there are no solutions to this equation. Let us see what we can do if before we go there, let us see what we do with this sigma 1 and sigma 2. We have two solutions, sigma 1 and sigma 2, which means that this means that both exponential sigma 1 t and exponential sigma 2 t are solutions to our differential equation. Now, when you have two possible solutions to a linear differential equation, the actual solution could be any arbitrary linear combination of the two. The complete solution will be a linear combination of these two, and the particular constants A1 and A2 are determined from initial conditions, and let us see how to do that. In our particular case, we have assumed that Vi falls from 1 to 0. Okay. Vi falls from 1 to 0. And V naught of t up to t equal to 0, it has a value of k. Now, if you notice this system, initially Vi is 1 and then it falls to 0, okay, and the input falls to 0 and the output is at k volts, and this is at V naught divided by k or 1 volt. Now, because there is a delay in the system, the input to the integrator changes. It is initially 0 volts when Vi and the feedback voltage are both 1 volt, and then Vi becomes 0. So, the feedback voltage is at 1 volt, but the feedback voltage cannot change for a period of Td. Okay. So, for a period of Td, any change that is happening here will not appear here. So, the output starts changing when the Vi goes down, and V naught divided by k also starts changing, but the actual feedback voltage does not change until a period of Td, until a time Td. So, what happens is, until a time Td, this feedback voltage will be held constant at 1 volt, and the input to the integrator will be held constant at minus 1 volt. So, I will show a period Td here. What happens is, during this period, the input to the integrator is minus 1 volt, which means that the output of the integrator goes down at a slope omega u until a time t equals T d is reached. And after this, this is V naught of t, and V naught of t minus T d is simply a delayed version of this. This starts changing the feedback voltage, and what happens is the slope starts reducing, and finally it can go to 0. I am only showing this qualitatively, I do not know exactly what it does, whether it goes beyond 0 or below 0, etc., but it is a sum of exponentials, it is probably going to go down like that. Okay. So, now we have two initial conditions with which we can solve the particular solution, and that is we can get the constants A1 and A2. So, at t equals T d, the value is, because the initial value is k and you have gone down at a slope omega u for t equals T d, V naught will be k minus omega u times T d. The amount of fall during this time is omega u times T d. Okay. And also at t equals T d, the slope is continuous. So, the slope has been omega u all along, and at t equals to T d also the slope remains omega u, that is minus omega u. Okay. The slope here is minus omega u. So, the value of the slope is minus omega u. So, we have two equations and two unknowns A1 and A2, and from these two we can calculate the particular solution. Okay. And I have shown a case where the input falls from 1 to 0, and it could equally well go from 0 to 1. Exactly the same procedure holds. The picture will be inverted. You can still equate the value of the output voltage and the slope of the output voltage at t equal to T d and find the particular solution. Okay. This is the general solution, and we have two conditions. V naught at the time T d is k minus omega u T d, which can also be written as k times 1 minus T d divided by omega u by k, or k times 1 minus tau, okay, where tau is the normalized delay. We also have dV naught by dt at t equals T d to be minus omega u, and this is for the particular case where the input is falling from 1 to 0. If the input is going from 0 to 1, it will be the opposite, but for any case you can find out the boundary conditions, apply these two conditions and find out A1 and A2. Okay. So, that is the way to solve any differential equation, and that is the method we have used here as well. Okay. Now, we can try to look at what kind of solutions we get for sigma as well as for the final differential equation. So, let me redraw the function sigma prime plus exponential sigma prime tau versus sigma prime. So, as we saw earlier, the first part of the function is a straight line passing through the origin, and the second part of the function is an exponential whose rate depends on the delay tau. Okay. And we also saw that if the exponential is very shallow, we will get two solutions to this equation, and if the exponential is very steep, we will not get any solution at all. Now, I can show you a neater picture obtained from a numerical simulator. This function cannot be solved explicitly. I cannot write sigma prime equal to some analytical expression. I have to solve it numerically. You can use any of your numerical tools to be able to solve this one. Okay. And if you want to apply initial conditions to your numerical solver, you can use the fact that the solutions will lie beyond sigma prime equal to -1. It will be more negative than -1. We can look at the solution here obtained from a numerical solver. Okay. Now, there are many curves here for different values of tau. The lowest curve, the blue curve, it is for tau equal to 0. Okay. That is no delay at all, and you see that its solution is -1, and there is only one solution. In fact, you can think of it as having two solutions, one at -1 and another one at -infinity. Okay. And you can see as the value of tau increases, the red curve here, is for tau equals 0.1, and the pink one is here for tau equals 0.2, and this is for 0.3, and so on. So, as you can see, as tau increases, the red curve is almost close to the straight line, and then it will come back up for much more negative values of sigma prime. The pink one is already going back towards positive values, and the orange one has already gone back to positive values, and you can clearly also see the two solutions. So, one of the solutions is here and one of the solutions is here. This solution is close to 2 and this solution is close to -6. This solution is close to -2 and this solution is close to -6. Okay. And I have also shown here a particular case for which the minimum of the function is just touching the x axis. So, for this there are again two solutions, but both the solutions are identical, and this green curve, the last one, is for tau equals 0.4, and for this there are no solutions. Okay. Is this clear? So, again we see that there is a straight line which is the solution for tau equal to 0. There is a straight line which is the curve for tau equal to 0, and the solution to that is -1. If you want to think of it as two roots, -1 and -infinity, and all the other curves start bending back upwards, and that is most clearly seen in the orange curve. There is a solution here and the solution there, and one way to think about it is the solution at -1 for tau equal to 0 is increasing in frequency, that is, it is becoming more negative. The solution at -infinity is decreasing in frequency, it is becoming less negative. Okay. So, that is what happens. So, now for these particular values of sigma, you can calculate the particular solution. Okay. And this value, the value of tau for which the function just touches the x axis, can be found out, and the way to do that is put down the function sigma prime plus exponential sigma prime tau. This is your function. Differentiate this with respect to sigma prime and equate that to 0. That will give you the value of sigma prime for which the function is a minimum, and you set that minimum itself to be equal to 0. So, that means the curve is just touching the x axis, and you can solve for the value of tau. Again, I encourage you to solve the problem by yourself before looking at my solution. Here I have shown the same graph over a much wider range. So, the orange one you see was here and the pink one folds back up and the red one also folds back up. Okay. So, for the red one of the solutions is very close to -1, that is the solution without any delay, and the other solution is something like -35 or something of the sort. As you can intuitively imagine, for very small values of delay, the behavior will be the same as that without delay. Okay. So, you can see the solution to the red curve is very close to the blue one, that is one of the roots is very close to -1 and the other root is close to -35. Okay. So, the two solutions due to the two values of sigma will be of the form exponential -35 omega u by k times t, and due to the other one exponential of minus, it is very close to 1, let us say 1.1 or something like that, 1.1 omega u by k times t. You can easily see that this function dies out very quickly, it becomes 0 very quickly and the solution is dominated by this function. That is to say, the final solution is very close to the case without delay. Okay. As the value of delay increases, the two solutions become close to each other. They also become quite different from -1. So, then something interesting happens. What is that? We will see shortly. Okay. Here I am showing an example of the solution that is obtained to the differential equation. This is obtained from a simulator. Essentially, what this is the solution a1 exponential of sigma 1 t plus a2 exponential of sigma 2 t with the particular initial conditions that are applied. In this particular case, I have used an input which goes from 0 to 1 by k at t equal to 0. This is why the output is going from 0 to 1, which is k times the input voltage 1 by k. So, you can see that it is going from 0 to 1. Also, the x axis is graduated in normalized time constants. 1 corresponds to k by omega u, 2 corresponds to 2k by omega u, 3k by omega u and so on. Okay. And the lowest curve here, this corresponds to no delay. Okay. So, this is simply nothing but this curve is 1 minus exponential minus omega u by k times t times k, okay, times k times the input voltage. So, 1 minus exponential, this is the traditional solution to the first order equation. And the next curve here, this is for tau equals 0.1 and this is for tau equals 0.2 and tau equals 0.3. Okay. Actually, what you see is rather interesting. It looks like, first of all, there is no overshoot, which we thought was a possibility. We were not sure, but at least for these values of delay, tau equals 0.1, 0.2 and 0.3, there is no overshoot. Overshoot means that the output is supposed to go from 0 to 1 and it goes beyond 1, and you can see that nowhere is it going to 1, and if I plot it up to infinity, it will not go beyond 1, it will asymptotically reach 1. Okay. So, and the second thing is that the response with tau equals 0.1 is actually faster than with tau equals 0. That is, a little bit of delay is helping the response of the system. You are going faster and faster, and this red curve is faster than the yellow one, and the green one is faster than the red one, and so on. And the very last curve here is for tau equals 0.3675, and this is the largest value of tau for which there is a solution, that is this corresponds to the function being a tangent to the x axis. Earlier we said that for very large values of tau, the function remains completely positive and there is no solution, and this tau equals 0.3675 is the highest value of tau for which there is a solution. So, the message to be taken home from here is that, first of all, for small values of tau there will be two possible sigmas. which gives you two possible exponentials as solution, and the actual solution in any case will be a linear combination of the two exponentials. Or more significantly, for small values of tau like 0.1, 0.2 or 0.3, the response A, it does not have an overshoot, and 2, it is actually faster than the response without delay. Okay. So, you can see that the yellow, red and green are faster than the black one which has no delay. So, it seems actually it is desirable to have a certain amount of delay in the system, so that you can reach the steady state faster. We will examine this in detail, and the highest value of tau for which there is no overshoot happens to be tau equals 0.3675. So, we will now see what this particular value is, how this value comes about. Okay. So, we were looking at this function sigma prime plus exponential sigma prime tau equals 0, and this is what we were plotting. Okay. Now, there will be no solutions to this if the function remains entirely positive. Okay. And this happens for large values of tau, and we said that the way to find it is find the value of tau for which the minimum of the function is exactly 0. Okay. So, the bottom of the curve touches the x axis and then goes back up. We have to find the minimum value of this function sigma prime plus exponential of minus sigma prime tau, and to do this we do the usual process of differentiation. Differentiating this, we get 1 minus tau exponential of minus sigma prime tau to be 0, and from this we get exponential of minus sigma prime tau to be 1 by tau, or sigma prime tau to be ln tau, or sigma prime to be the natural logarithm of tau divided by tau itself. This is the value of sigma prime for which we get the minimum value of the function, and the minimum value is obtained by substituting the value of sigma prime into this one, and that will be okay, and we want to find out the value of tau for which this is 0. Okay. This gives us ln tau by tau plus exponential of minus natural logarithm of tau, which is 0, or the natural logarithm of tau is minus 1, or tau is 1 by e. Okay. And 1 by e is 0.3675. When the natural logarithm of tau is 1, or tau is 1 by e, the natural exponent, we will have a case where the function sigma prime plus exponential of minus sigma prime tau just touches the x axis, and we have two identical roots. And for tau greater than 1 by e, we have no real solutions, and we have to resort to complex solutions to this particular function. That we will see in the next lecture.